Hello, stat students. Welcome to Chapter 3. Chapter 3 is called Data Description. So we're going to start actually doing some calculations. Data description is calculations. What does that mean? Chapter 2 was about graphical ways to represent your data. So now we're going to get into some more technical calculator types of things. So first of all, the term average, we all know the word average, we use it a lot. It falls under, people in general use it as kind of a generic term. Average is actually mean, and it falls under one of the measures of central tendency. So our measures of central tendency are mean, median, mode, and mid-range. And let's talk about each one of those. So quick review. First of all, everybody knows parameters and statistics, right? Well, we don't need that. Don't write that down. Just kidding. So let's try this again. Parameters and statistics. We know that a population is all subjects of interest. All, right? And they may be humans, animals, businesses, blah, blah, blah. We said this back in Chapter 1. And gathering data is typically time-consuming or expensive. Think about the 2020 census. It is a months-long project to try to get data from every single household in the United States. So, parameters are usually inferential, and they're measures found by using all the data values. So we might be looking at gender. We might be looking at household income. We would use that data from all of our values in a population. However, typically, we need to use inferential statistics with a sample and a sample statistic. So population parameter, population is all subjects. The parameter is what we're interested in. And samples are the group of some subjects. Remember, we want this to be representative. Otherwise, it's a biased sample and it doesn't represent our population, so we can't make an inference from that. Our statistic is the measures found using our data values from the sample. So maybe we take a sample of 100 people and we say, here's the breakdown for household incomes, and then we would make an inference and we would apply that to our population. General rounding rule, we've got a lot of stuff happening, a lot of calculations starting with Chapter 3. So first of all, only round after your final answer is calculated. Do not start rounding things and then using rounded numbers. Hopefully you've heard your math teachers say this, especially as you get into higher level math. I know I said it in geometry when we were doing calculations with like volumes and surface areas. Only round at the end, don't round along the way. We get less and less precise as we go. We want to be as precise as possible. And round the calculated value of the mean to one more decimal place than the raw data. So if all of your raw data is whole numbers, your mean, you would go to one number after the decimal. Right, so it's one more decimal place than your raw data. Hopefully everybody knows what I'm talking about with raw data. Raw data is the actual data that you collected, and then we turn that into proportions and now measures of central tendency. So let's start with the mean. That's a review thing, new thing about your rounding rules. Hopefully that all makes sense. The mean is our arithmetic average, right? We use the term average a lot. In stats, we're going to call it the mean because a lot of times the general public, the average can mean a lot of things. We want the mean. We know how to find the mean. We add the values of the data, divide by the total number of values. Now we're going to start to be really specific. If you notice in the notes, we've got population mean and we've got sample mean. There is a difference, right? Population is your whole population. We have, here's our first term. We use this little letter. Previous years, they wanted me to teach them how to write that. It's like a little U, maybe a small cursive U with the extra tail at the beginning. You say it mu. It's a Greek letter, mu. Mu always represents the population mean. So this is huge. I'm going to probably even just say mu, and you're going to need to know what that refers to. It's calculated by using all the values in the population. You can imagine if you've got a large population, you're going to have a lot of data values. And here's our formula. You know it. Notice now I'm being technical. I'm saying in this third bullet, mu is equal to x1 plus x2 plus x3 plus all the x's or all the data values all the way up to your final one, x to the n. Notice capital N, and that's all divided by n. I prefer this formula because you're going to understand this way better. That's a lot of writing. I like this. Sigma x over capital N. So our x, each x value is a data value in the sample. This should be a capital N. Please change that. I fixed things later. Capital N is the number. I changed that poorly, right? Capital N is the number of values in the population. And the little E looking thing is sigma. It's a capital S or capital sigma. And that means sum of. So if we say sigma x, we're taking all of our x values and finding the sum or adding those all together. It's a lot shorter way to write than x1 plus x2 plus x3, blah, blah, blah. We're dividing by n. So what we're doing is we're adding up all of our x values, all of our data values in the, population. Really messed that up. And dividing by the total number of values in our population. It's our formula. It's technical. You know how to do this already, but there's a lot of, this is where at the beginning in this syllabus I said stuff, there's a lot of symbology and terminology. Those symbols are going to be important. You're going to need to recognize them, know them, and know how to say them. So our first symbol is mu, which stands for population mean. We already know n. Notice it's a capital if it's a population. We're going to use a small if it's a sample. Sample mean is what we'll work with most frequently. Sample mean is denoted by x with a little bar over it. It's called x bar. So anytime I ask you about x bar, you're going to know, oh, she's asking me to find the sample mean. I probably have my box stuff messed up over here. So x with a bar over it. It's technically a capital X. So our sample mean, we all know we use all the data values in the sample. Hopefully it's a little smaller than the number of data values in the population, but you could have something you're looking at that has a small population. I could just use my virtual students as my population. I would have, maybe 13 pieces of data. So here's our formula, this third bullet, x bar is equal to, notice I did the same thing. I can do x sub 1 plus x sub 2 plus x sub 3, keep going until I get to my final data value, x sub small n, and that's all divided by n. And we all know that n is the number of data values in the sample, small n. Boy, that's a real screw up, sorry. X is each data value. So we add up all our data values, we divide by the number of data values that we have. So difference in the formula, and if I had my boxes all correct, capital N versus small n. Let me do it this way. Capital N is population. Small n is sample. I could say X is my data value for both. I could say population, I use mu. Sample, I use X bar. You see any other? I think that's about it, right? So I've got an example in here. The data represents the number of home insurance claims last year for each town in St. Clair County. Find the population mean. Notice it asks me to find the population mean. What's my symbol for population mean when I do my calculations? I'm going to have mu equals, and you're going to add up all of those. What is my N? Notice this is going to be capital N. Capital N is the number of pieces of data in my population. 1, 2, 3, 6, 9, 12. I believe my population sample size, or my population size, is 14. Can everybody figure that out? You know how to do the calculations, add them all up, divide by 14, you've got your mu. So watch. Notice, I've got another example. I think I've used the salary of college coaches and university coaches. Data are salaries of a sample of 30 coaches. Find the sample mean. So if we were going to do this, we would be finding X bar, and we would be using small n is equal to 30. We would add up all 30 of those pieces of data, divide by 30 to get our sample mean. So I know you've been doing these calculations, you know how to do this, but it's all about the symbols and the terminology. So I don't want to drag it out too much, but you know. So let's talk about, everybody knows how to do that, but what if I give you a frequency table and I say I've got this grouped data? We don't know every single piece of raw data, so I've just got a frequency table. I'm only going to use this for a frequency table. If you do not have the raw data, this is your go-to. So no raw data, we've got grouped data. When I say grouped data, I'm talking about I've got classes from 140 to 229. I don't know each individual piece of those 11 pieces of data. I just know that 11 pieces of data fall into that class. Notice I'm still using X bar. And in order to do this, I got fancy on you here. I didn't write out all the stuff. I'm going to use, it's been only a couple minutes, but do you remember what sigma stands for? Right, find the sum of, that is sigma. So sigma of, you're going to find the sum of your F, frequency, times your X sub M, midpoint for each class, and divide by N, your sample size. Should I put N on there as well? N equals sample size. The formula can look intimidating because we're new at this, but we can do this. So what we're going to need to do is we're going to need to take out a calculator and do a little bit of math. What I need to do first is find all of this calculations. So frequency times the midpoint, and then I'm going to add all those up. Notice I made a table here, so it's all there. I'm going to add those all up and then divide by N. So if I go to my table, my class limit from 140 to 229, all I know is that I've got 11 pieces of data. Thankfully, I already did the math and I got your class midpoints for you. So I'm going to do frequency times midpoint. So I'm going to go to my calculator. I'm going to do 184.5 times 11. And correct me if I'm wrong, but it looks to me like that's 2029.5. If I have bad math here, shoot me a message, let me know. I can't always see my little tiny writing. So I'm going to do the same thing for each one of these rows. I'm going to take my frequency, multiply it by the midpoint. It looks a lot more confusing than it actually is. We got this. So 274.5 times 5. I've got 1372.5. Take a quick minute, hit pause. I'm going to hit pause. I'm going to put in all my math, and then we'll talk once we get all of our frequencies multiplied by our midpoints. All right, double check all your frequency times midpoint. This is what I've got. I didn't go any further because I want to refer back to this formula. It says we're going to take all of our frequencies times midpoint. We're going to add them all up. So I'm just going to go down this column. I'm going to add up all of these guys. Sigma means add. And find a total. I'm going to put it in that little box at the bottom. I believe that's 10,395. Whoops. 10,395. So if I'm going to do my formula, I'm going to do my sum of my frequencies times midpoints divided by n. And I am going to get a mean or an x bar of 364.5. 346.5. So here is my final answer. It's not as exact if I had raw data, because all I know is I've got group data. I don't have exact detail or exact data points, but it's all right. So I do want to make sure I mention down here in this little note, your calculated mean may or may not be an actual data point. I don't know if 346.5 was an actual data point. I know that it's going to fall somewhere in this class, but that's the best I can do. As a matter of fact, I would be willing to bet that that's not an exact data point because I don't have decimals. Notice my class limits all have whole numbers. So I didn't have any decimal data. Class limits always have the same decimal values, same decimal point numbers of decimals as a data does. So again, only use this if you're given a frequency table. Do not use this if you're given raw data. If you're given raw data, you know how to find the mean. Sum of your data divided by n. All right, so next up, let's talk about the median. I hope everybody knows what the median is, the center or the middle of an ordered list of data. So in other words, yes, you have to put these in order unless I very kindly typed them in order like practice 4. Probably is not going to happen every time. The symbol is MD or MED. I usually use the MED, median equals. So a couple of things. First thing I'm going to ask you is, I'll assume this is a sample. What's my data, or what's my number of data values, or my n, my sample size? I think it's 36. If your n is an even number, that means you're going to have two numbers in the middle. So if I am looking at this, you can work your way in. I can divide by 2. I can say 18. I can count 18 from both sides. I believe that the middle is going to fall right in between these two values right here. So this would be the median. But of course, that's not a bit data value, right? So what I'm going to do is I'm going to take the ones on either side. I'm going to average those guys out. And you might be shocked to learn that the midpoint or the average of 130 and 130 is 130. So my median is equal to 130. When we go further, those data values get thrown out because we've used those for our median. If you've got an odd number of data, then you're going to have an exact data point in the middle, so there's no averaging needed. The mode is our next thing to talk about. A mode can be used for qualitative data, like what shows up most frequently or most often. But we all know, hopefully you remember from back in the day, that the mode is the value in the data set that occurs most often. So this can also be used for quality or qualitative data. So if you remember back in chapter 2 when we talked about shapes of data, we talked about bimodal. A graph or a histogram looks bimodal. Well, that's because it has two modes. So unimodal is one value. That's typically our data, but a lot of times we do have data that shows up more frequently. Bimodal, you might be shocked, is two values. Multimodal, I typically say more, it says more than two, but I'm typically going to set that at 3. Because no mode is when you have so many of the values occurring most frequently. You have a lot of repeats. It's just not even worth saying. So we would say 1, 2, or 3 modes. Other than that, we're going to say it has no mode. No mode is probably going to look like a uniform or a flat histogram or graph. A modal class is, in a frequency table, the class with the highest frequency. So this is all raw data. If I give you a frequency table, We can only say, all right, well, this class has the highest frequency. We can't say an exact piece of raw data because we don't know it because it's lumped into a class. So I could ask you, I could say, here's a frequency table. What's the modal class? And you'd say, oh, from 15 to 22 is the modal class. That's the best I can do. So I don't know how you feel, but I feel like we don't really need to practice finding the mode, what shows up most frequently. We can look at the data. Notice if you look at these two sets of data, they are not arranged numerically, so median would be a little tricky. Mode, we're just looking for what shows up the most often. When I just glance quickly at B, 109 shoots out at me. Don't know about you, but, and it looks like in letter A, looks like I have 3 10.0s. So it looks like those would be the modes. All right, so if we find the mode for this, fast food franchises, the mode is the one that shows up the most often. There is no mode here, right? Because there's no repeats of anything. All right, mid-range, MR. I don't actually say mid-range. Mid-range, do not get that confused with other things or like midpoint. This one's a little sneaky. It is the mean of the highest and the lowest values in the data set. It has the word range in it, right? So we know how to find the range, highest minus the smallest. So then we take the midpoint of that, or not, the mean of that. So it's the midpoint of our range. We can estimate if we've got a uniform or a flat distribution. I don't know. I mean, if we've got raw data, we might as well just do the calculation. So this is interesting, right? When you find the range, you do highest minus lowest. When you find the mid-range, you add your highest and lowest and divide by 2. Just like when we find the midpoint on a frequency table, we add our class limits and divide by 2. So a lot of times people get messed up. Do I add or subtract? If you're just finding the range, range is highest minus lowest. Mid-range is high plus low, divide by 2. So just watch out for those. That's a little sneaky. All right. So our measures of our resistant measures of central tendency. So central tendency is mean, median, mode, and mid-range. So there are some resistant measures. They don't affect, there's things that affect or do not affect our stuff. So extremely high or low data values doesn't affect our central tendency. They kind of just work their way in. We call them outliers. They're kind of messy, big or small numbers that could mess up our data and could mess up our histograms or our frequency tables. The median and mode are resistant. Because for mode, what just shows up most often, for median, we work our way to the middle. So any high or low value is going to just kind of go away. However, mean and mid-range are affected because mean, we use the individual pieces of raw data. Mid-range, we use high and low. So one of those is going to be an extreme value. So those are going to mess up our mean and mid-range. So median and mode are very resistant to these crazy things. So in practice number 8, if I say find the measures of central tendency, it says find the measures of central tendency with these. So this would be data set 1. Find the measures of central tendency without this extreme value. And the extreme value in this case would be 240. It's extremely high compared to the rest of my data. Here's the thing. You might be asking, how do I know that that's an extreme value? Well, you know it today because I'm telling you. In this chapter, we'll talk about where you find those extreme values. We've also got our outliers. We'll talk about how to find outliers. There's a couple different ways. So this would be data set 2. I feel like I don't necessarily need to go through all the practice stuff because you can find these, but it's just to kind of give you a comparison because I would be willing to bet that your median and mode are not very affected even with the 240 in there, but your mean and mid-range will be a little bit messed up. So just kind of a comparison thing. I hope I'm not skipping over all the examples and it's not good for you because I feel like you've done this stuff and you can figure this out as we go. So shapes of distributions. We talked about right skewed data. If you look at this, this sort of looks like it could be a bell curve, but these guys over here are kind of pulling it to the right. So we call it positive, the positive direction, or right skewed data. And most of the data falls to the left of the mean. So notice here is the mean right here. So most of our data is on that side. It's getting pulled to the right. Our data clusters at the lower end, and the tail stretches to the right. This is the key thing right here. This is what makes it right skewed, or positive direction. And the mean will be to the right of the median. The mean will also be to the right of the mode. The mode will be farther to the left. The average, or the mean, gets pulled by our extreme values, or our outliers. If we look at negatively, or left skewed, notice this looks like it could be a bell shape. However, we've got these guys down here that are pulling to the left. That's why it's called a left skew, or the negative direction skew. This is the exact opposite of right skew. Everything flips. So notice my mean, median, and mode switch the order. I can put this stuff in here, or you could just say the exact opposite. Exact opposite of right skew. Feel free to not write down these things if you just want to say it's the opposite. Notice, though, I put this picture on purpose. The mean gets pulled to the left because of outliers. Our mode will still be in the middle where that bell curve would be, and our median is farther to the right of the mean. Here's the one I like the best. Here's our symmetric, or bell, or I think I might have said I call it a normal curve a lot. That gets into semester 2, and I forget what semester I'm in. So notice this is a symmetric, or a bell curve, and it's got nice, remember, not everything's perfect, but it's got nice potential to be perfect bell shape, very symmetric. Data values are distributed evenly on both sides. And the nice thing about this is it's unimodal. We've got one mode. And everything is equal. The mean, median, and mode are equal, and they're at the middle. These are like the perfect curves for stats. Everything is symmetric, even, in the middle. The mode is in the middle. The mean is in the middle. There's no outliers. There's no crazy things pulling to the right or to the left. The data values fall right into place. It's going to be interesting when you're working on your quarter 1 project to see how that looks, see what it looks like when you collect your own data. But we'll talk about that project separately. All right, that is it for section 3.1. Thanks for sticking with me. I know the concepts were relatively easy, and hopefully a review or a dredge up some old memories. And then we throw in that extra stat stuff for you just to keep you on your toes. So remember, we're not calling it average, we're calling it the mean now. So, and get to know your Greek letters. Sigma is the sum of, mu is the population mean, x bar. Those are all important. I'll probably shoot you a little symbol sheet so you can keep track of things. That is it for section 3.1. Thanks for sticking around.